actually very lucky to have Greg with us here today because we've been trying to secure him for a very long time now, and finally we have got him here with us tonight. Tonight's presentation is on the design of timber connection using screws, and Greg Pankhurst is the technical consultant engineer for SPAX, the world's leading manufacturer of timber connection screws. He's a Bachelor of Engineering degree from the University, UTS in Australia, and has more than 20 years experience in engineering and marketing within the fastening industry. Consists of 22 years as field engineer, product manager for Hilti Australia, and marketing manager for Hilti New Zealand. His current role is focused on advising and assisting consultant engineers on timber connection design, increasing the market knowledge, and partaking in research with the tertiary organizations. So without further ado, please welcome Greg Pankhurst. Thank you.
All right. Thank you very much for that introduction. Thank you for inviting me here. It's a pleasure to be here. Always love being in New Zealand. I lived in New Zealand here in Auckland for about 3 years, back in 2000. So I always enjoy coming back. My daughter married a Kiwi, so our first child was we call a Mozzie, so half Maori and half Aussie. So, all right. So as I said, my name is Greg Pankhurst. So I'm the engineer for SPAX, or SPAX Pacific. I look after Australia and New Zealand for SPAX. So we just want to go through a few design principles, etc., for screws into timber tonight. So what we're going to cover, just very briefly, but it's introduction to SPAX, the different connection types, different applications you can use screws for. We'll have a look at some case studies as well, design considerations to what you need to look at when designing with screws, a few examples, and we'll compare a little bit with NZS 3603 compared to the Eurocode. And you'll see how they match up. So briefly on SPAX. SPAX was founded in 1823 under the name of Alton O'Brien and Company. So the company ABC still exists as that. SPAX as the traditional timber screws was actually formed a bit over 50 years ago. So that was a breakaway from ABC Company. So SPAX has been manufacturing screws for 194 years. We are the oldest screw manufacturer in the world. We are the leader in timber screw technology in in Europe and in the US as well. We're not a small company. We produce 50 million screws per day in our German factory. Turnover about 400 million, 1,400 employees in Germany itself, about 3,000 worldwide. So we only have about 13 or 14 employees in Australia and New Zealand, but growing rapidly. So still young. We've been here about 13 years, but as I said, growing rapidly. So a lot of room for expansion as well. I know a couple of you may have seen some of this presentation before. I can see a couple of familiar faces, so apologies if you have. And if you know quite a bit of this timber design as well, I'm going to assume that you know very little. So bear with me as well on that. So, but basically SPAX, being a German company, we pride ourselves on innovation. So our screws have various points of difference compared to others or compared to traditional screws. Starting from the point down, you'll see what we call a four-cut point. That's like a square shape on the end. And that's designed to spread your fibres apart in your timbers and puts less stress on the timber and there's less chance of splitting. And the serrated thread on those first few threads basically cuts through your timber, and that means you get less torque required to insert the screw, and again less chance of splitting. The head is what we call or the insert bit is called a T-star plus, a little bit different to a normal Torx drive. It has a sort of dimple on the end. It gives you very good torque transfer into your screw, and the guys on site that use that absolutely love it. So, the other main difference is the coating. The coating is what we call Delta Seal. Now, Delta Seal was originally made for the automotive industry. In this case, it's actually zinc plating underneath, and on the top it's an epoxy coating. So that makes it ideal for treated timbers, so it's resistant to your chemicals, and for harsher environments, the corrosion protection is twice as good as hot dip galvanizing. So if you look at the torque versus time, so screwing torque on the vertical axis and time on the horizontal, you'll see the SPAX screw there is the torque is about half as much as a traditional timber screw, and it's also quicker to install. Okay, you do pay a little bit more for the screws, but you're getting the quality, and you're getting a faster and easier installation. So what we find is that once installers start using it, they love the screws, and they won't use anything else. So, and as I said, everything is made in Germany. So we've still got the original plant. So obviously it's expanded quite a bit and modernised, of course, after 194 years. So made in Germany, we can guarantee the quality of the products. We can provide a certificate of origin as well, what we call a TÜV certificate. And so we have a clear commitment to the quality and security of our products. I went over to the plant, the factory, beginning of last year. I was just amazed at the quality control. Every single step of production, they're checking. And if something goes wrong, they get rid of the whole batch since the last check. They have computers checking the threads and everything like that. And once it comes back from the platers, it's checked again. So, okay. Everybody likes to see a few projects, case studies. So I thought I'd throw a few in here just to give you an idea of what you can do in timber. This is a wooden roller coaster in Sweden. Quite an amazing sort of structure. Some of you may have seen the Amiga, the Swatch headquarters in Switzerland. Anybody seen that? Yeah. These are early sort of artist impressions, but I believe it's pretty much finished now. There are millions of SPAX screws used in that project. A couple more local ones. You would have seen the Macquarie University Innovation Hub won a design award a couple of years ago. Knoll Ridge Cafe at Whakapapa. Waitomo Caves Visitor Centre as well, all SPAX screws. Catholic School in Sydney, Bunjil Place in Melbourne, won last year's Timber Design Award. That's an amazing structure as well. Maya Timbers warehouse in Penrith. I don't know if you can see that very well, but quite large spans for your timber. And how it worked was, you'll see it's like a tongue and groove connection. So your tongue basically fits in here. You'll see this is cut out there, so, and it's just joined with all these SPAX screws around it. So that was a very clever design as well. Otago Polytechnic down the South Island. There's a lot of screws in that with XLAM as well. Housing New Zealand, so they're using all SPAX screws for that as well with the CLT. The new one is just starting this month, which is Iron Creek, Tasmania, which is a backpackers hostel. And that's my backyard. So we use SPAX screws anywhere. So. Okay. So when you're looking at screws, there's different connection types you need to be looking at. Other areas like bolts, steel plates, coach screws, gang nails, things like that can be replaced these days with a modern screw. Now, what are the advantages of modern screws these days? You're looking at aesthetics as a major one. So instead of having plates in a situation like that, you can use screws which are completely concealed, and you get a connection that looks like that. So that was actually at Bunjil Place in Melbourne, those connections. So using a lot of fully threaded cylinder head screws in those. So aesthetics is one advantage. Another one is fire reaction. Your screws can be driven inside the timber, driven below the char zone of your timber, so they're fully protected from fire. They're good for earthquake situations, for seismic. They are ductile connection, so obviously ductile connections are preferred in most situations that way. So speed of application, they're a lot quicker to install than a normal like bolts and plates, etc. They're a more rigid joint as well. So instead of a bolt, you might have a bit of a gap between the timber and your bolt. Where you screw, you don't have that. So it's a very rigid connection. They're also a cost-effective alternative to both bolt connections, metal parts, lateral reinforcement, glued-in reinforcement panels and things like that. So they are very cost-effective in that way. So some different applications where you can use screws. This is what we call a post and beam application. So what you're doing here is using a partial thread screw to attach your beam to your post. So you can see here the thread is completely in the post, whereas the shank is in the beam. The idea of that is to clamp the two together. So if you use a fully threaded screw in that to start with, that's going to draw them both apart, and you won't get a tight fixing. So in the post and beam application, start out by putting a fully threaded screw in to clamp them together. Then for a strong connection, you put in fully threaded screw at a slight angle. So we recommend a minimum incline of 15 degrees into an end grain. Hilti doesn't like seeing screws going directly parallel to the grain. There's too much of a risk for sudden failure, and you don't know how it's going to react with expansion and contraction, etc. Having said that, we've just done some testing in end grain, which has some interesting results which should be available soon. So what happens with that one, it's giving you a real strong connection. So your strength is coming from the full thread screw. Okay, so there's 4 fully threaded screws inclined, giving it an incredibly strong connection. Once those screws are in place, you can then remove that partially threaded screw, the washer head screw, because that's basically not doing anything after that. It's done its job. You do the same thing with your bracing, whatever, as well. Another application that's becoming more common as well is a joist and beam application. So joining your joist and beam with diagonal screws, crossing like that, or the bottom one you can do parallel. That's a little bit more difficult, incline screws in like that, because you're embedding your screw a fair way into the timber. And it's a little bit more difficult to getting a drive bit that long to do it. So the most common way is the one at the top there, when you're crossing your screws in that application. So that's ideal instead of using L brackets or plates of any type. For CLT and LVL connections, common ones are half-lap joints. Floor-to-wall applications. The X-Lam air stair is quite a common one as well. Wall-to-floor applications. In that one here you can see screws going in diagonally. So you can use those instead of brackets for that application as well. So they're all hidden. Corner walls, wall-to-floor. So any joints in CLT and LVL, very easy to do with your screws. Tensile reinforcement is another common application for fully threaded screws. So with a notch beam, something like that, hang on, go back. You get the situation where your weak point is here, and it'll tend to crack from that point backwards. So this will show you
10,
what happens in that case.
15.
Das steigt der Druck nicht mehr, ne?
Nee.
Ja. Der Riss wird sich auch so weiter fortsetzen.
No, that cracked very quickly. So it was only very low load as well. It's probably around about 10 kilonewtons before that cracked. Okay. So to overcome that, that's your weak point. How do you fix that problem? You screw, put a fully threaded screw in as close as possible to the notch. So that's going to hold your timber together and stop it from cracking. So you can put it in beforehand to stop any potential crack, or you can put it in afterwards to hold it together after it's cracked as well. Obviously you don't want it to crack in the first place. So in this case, this side was already reinforced before, so they put a couple of fully threaded screws in this side. So you'll see what happens now, and have a look at the load when it's
10,
happening as well.
15,
Just the same piece of
20,
timber. You can see where that crack was.
30, 35, 40,
You can see that bending as
45,
well.
50,
Ja, ja.
55,
Stopp mal ganz kurz. Sie sehen jetzt auch schon, wie sich die Stahlplatte ins Holz eindrückt. Also die kommen von überall fest und entwickelt zur Faser jetzt schon maßgebend wird. Ja, machen wir weiter, das fehlt ja noch. Der Riss geht auch
hier wieder bei 50,
weiter oder so. Ne?
55, 60,
I hate to show, there's nobody from workplace health and safety, is there? They don't seem to worry about it so much in Germany, I don't know. But yeah, so you can see what happens when you reinforce your notch beam like that. So it got up to about 60 kilonewtons. So a big increase in load as well. So other applications where you can reinforce is this one here. We're using a bracket, what have you, to stop you cracking there. Stop any potential cracking in reinforcement, in penetrations in glue lam beams, for example. So, you know, your potential crack would be along here in those cases. So, there is information in the Eurocode and the ETA on how to design for that, for reinforcing in that area. Bent glue lam beams as well. They might tend to delaminate at some stage, so reinforce it with screws. We have actually a 16mm diameter screw as well. It's specifically used for that application, made up to 3 meters long as well. So reinforcement in compression as well, becoming more of an issue as timber buildings are getting taller and taller. What's going to obviously happen, if you get too much load on your timber, it'll crush like that. So putting fully threaded screws to reinforce it in compression, you don't get that crushing. So without the reinforcement, in this case there was 60 kilonewtons loading. With the reinforcement, there was no damage at 100 kilonewtons loading, which is the limit of the test machine. Okay. So what are your considerations when you're designing with screws? So we'll go back to basics. So if you already know a lot of this, just bear with me, okay? So some of the factors to consider, obviously grain orientation. So you're going into the side grain or you're going into end grain. Timber species and density. The denser the timber, the higher the load capacity, generally speaking. Edge distance, end distance and spacing all needs to be considered to prevent splitting and cracking, etc. The connection type. The connection type will determine the style of the head that you're using and the thread type, which we'll cover in a moment. Corrosion resistance obviously needs to be considered. Okay, where is it? Is it next to the sea or inland? Aesthetics, do you want the screws to be hidden? Fire resistance we've mentioned, and ease of installation. So selecting your screws, there's a couple of considerations. One is the head type. So there's a few different head types for screws. A washer head is a large head on the end. It's got a large bearing area, ideal for clamping pieces together. A countersunk head for flush fixing. Cylinder head is used when you want to drill the screw in deeper into the timber below the surface. And a hex head is another variety as well. The thread type you need to determine, it depends on your application. So you saw before in that post and beam application, partial thread is used for clamping your timbers together, and a full thread is used for a strong connection. A little bit more information on that in a moment. And the coatings, as I mentioned, you need to be looking at. So, full thread or partial thread, which one are you going to use? So your full thread is more for your longer screws. It doesn't have a clamping effect. They have very high load-bearing capacity, particularly in tension, but also in compression for your reinforcement, etc. Incline screws can work as a frame truss, ideal for reinforcement, and the screws come available up to about 600 millimeters long. Partial thread, as I said, is for a clamping effect, for pulling pieces together. The washer head will give you a much better clamping effect, but your countersunk head will give you a flush fixing. Okay, a bit more on the technical side of things. In terms of withdrawal, there's 3 different failure modes. So the first failure mode is thread pull out of the wood. Second failure mode is the tensile strength of the steel, of the screw. So if the thread is long enough in your screw, the tensile strength is going to govern. So your screw will actually break if it's long enough. And failure mode 3 is head pull through, which is the maximum of either the actual head or the thread pulling through. I'll come back to that in a moment. So if we look at an example of a connection collar or beam hung under a purlin, so you're looking at 2 8 by 400 millimeter fully threaded screws in this case. So your failure mode 1 is thread pull out of this, your base timber here. And this is the formula that you use, or the equation. So the FAX RK is your characteristic withdrawal capacity of the screw at any angle to the grain. You then look at the effective number of screws. If you have more than one screw, you may have to reduce it slightly by this factor as n to the power of 0.9, just because of the effect the screws have on each other. FAXK is your characteristic withdrawal parameter, and that may vary depending on the diameter of the screw. D is your outer thread diameter. L is your penetration of the threaded part into that piece of timber. That one is your characteristic density of the timber. You notice it's over 350. So 350 is the European, that is characteristic density, whereas the New Zealand code looks at design density. So there's a difference between the two. I'll come to that later as well. The alpha is your angle between the grain and the screw axis. So you don't have to go through that equation every single time you're designing a screw. Okay, it's all tabulated for you. So you can use this, which gives you withdrawal in newtons per millimetre of thread, and this one here is a reduction factor for as you go out down to 15 degrees to the grain. So easy to design in the end. So that's the Eurocode. If you compare that with NZS 3603, and not exactly sure how long that's going to last, with NZS 1720 coming out at some stage, probably still a little time off yet. So we're still looking at NZS 3603. That looks at failure mode 1, which is your thread pull out. It gives you your formula there, number of screws, capacity factors, modification factors, etc. Not modification actors, okay. So comparing the two with the ETL, the Eurocode versus 3603, with those different equations, you're looking at Eurocode's 25.6 kilonewtons and 3603 24.2. So not a lot of difference between the two in this case. Okay, that might vary depending on the type of screw you're using, the diameter, etc., and length. But in this case, not a lot of difference. And even the safety factors, modification factors, are not a lot different either. So you're getting a very similar result in the end. Your tensile strength is obviously not going to vary. Your steel doesn't vary between the two codes. Failure mode 3, as I mentioned, is head pull through. So you have either, so it's the maximum of the two. So that one is actually head pull over. So your timber is trying to pull over the head of the screw. All right, so that's your equation for that one. Or your timber is going to try and pull over the thread of that section. So obviously if it's only a partially threaded screw, that's not taken into account. It's only that first part. So generally this would be your maximum out of the two. So it looks at the maximum of those two, not the minimum. Why is that? Because once, if this tries to give way, that is still going to hold on to it. Okay? Yeah. So you're looking at, yeah. I won't bore you with that. The NZS 3603 doesn't really look at head pull-through. It does if you search through, and you'll find this equation in there as well, which looks at the bearing area under the screw head and a stress factor as well. So you can calculate it, but it's not easy to actually find that and do it. So most of the time it's actually ignored in the design, which it shouldn't be. It's quite often the actual failure mode in these applications. So if you're looking at the Eurocode, in this case it's the maximum of these two, 1.85 or 8.8, okay, and 3603, 1.98 versus 8.7. Again, so very similar. So okay, so in that application we were looking at before, just summarising your failure mode 1, you had those 25 and 24 up the top, tensile strength of 17, your head pull through 1.85, 1.98, and then 14.3, 13.6. So the minimum of all those is not that one, but it's this one here. 14.3 for the Eurocode, 13.6 for 3603. And then applying your modification factors, safety factors, you're down to these figures. So, as I said, very similar results between the two. Okay, don't worry about that. There's quite a difference when you come to shear. You're looking at, in shear, there's, in the Eurocode, there's 6 different failure modes. The best failure mode you can have is this one on the end. There are all these different equations for determining your shear capacity of your screw. This is what we call Johansson's yield theory. So I won't go through all that, but you don't have to calculate all those. It's all basically tabulated for you, and you can just work from tables. In shear with the Eurocode, you have an added extra bonus, which is called the rope effect, which is not considered in 3603, which is where the head of the screw acts basically like a piston or piston rod, and it resists any force. As that screw is trying to shear, that head is preventing it from going any further. So you get that effect of it pulling back on your timber to stop it from shearing as well. So I'll show you in a moment. On the other end, you're getting the thread acting in the same way. So the rope effect is really a quarter of your tensile capacity, or your withdrawal capacity of the screw. So that is added to your shear load or shear capacity of the screw overall. So this is a bit of a demonstration of what happens when they're in shear. It shows you it's also a ductile connection. Then you see that head is resisting movement of the screw, and the thread on this end is resisting as well. So that's adding to your shear capacity. Do that. So if we look at an 8x120 washer head screw, for example, so characteristic shear capacity per screw just going from tables and what have you. 2.59 in the Eurocode versus 2.63 for the 3603. But adding the rope effect gives you an extra 1.44 kilonewtons. It's giving you 4.03 kilonewtons all up for the designer by Eurocode. So, and that, comparing with 2.63, is quite a big difference between the two. So that's where your major difference is between these two codes. When pre-drilling, in shear, you can actually get an increase in load capacity with the Eurocode. So you can increase that up to 5 kilonewtons, whereas a 3603 does not consider that. 3603 actually says your holes must be pre-drilled, whereas Eurocode basically says that assumes you're not pre-drilling. If you're using a countersunk screw with the lower head pull through, you're going to get a lower rope effect and therefore a lower shear capacity. So 3.35, and again 3603 doesn't look at your different head types because it doesn't consider the rope effect. So same capacity. Designing for incline screws, using an 8x260 cylinder head screw. It's a minimum of withdrawal of the threaded length in beam 1. Beam 1 is this one here, so you've got your cross screws. So your threaded part in that beam, calculate that 13.6 kilonewtons. And withdrawal of the threaded length in the joist. So in your beam here, your screw is basically 90 degrees to the grain, whereas on this one here, your grain is going this direction. So that's 45 degrees to the grain. So you have a reduction factor on that. So it ends up being 12.3 kilonewtons. Tensile strength of the screw obviously doesn't come into it. Head pull through doesn't come into it either. And then you have a verification on here as well. Okay, so it's very simple actually to design incline screws in a joist and beam application. 3603 doesn't really look at that sort of application either. That sort of application was used in this project there in this house as well. So again, you can't see the screws at all. Spacing and edge distances actually work out similar in many ways, but yeah, if you look at the Eurocode versus the 3603, the main differences, Eurocode looks at the thread diameter and 3603 looks at the shank diameter. So something you need to be aware of as well. If you're designing with Eurocode, you can't swap over halfway through to NZS 3603. You can't combine the two. It has to be all one or the other. So there's a few differences there. Probably the main one is the spacing parallel to the grain. Yeah, and 3603 doesn't actually consider the direction of the load either. So Eurocode looks at the direction of the load, whether it's going towards the edge or away from the edge. So it's a bit more complicated, but it's much more logical. So it's a better way to do it. And okay, so that's actually looking at an 8mm screw, and that gives you some factors, all your actual distances. So parallel to the grain, Eurocode's actually better. Perpendicular to the grain, 3603 is better. So it just depends on the application where you're using it. Okay, So, with modern screws these days, generally they're self-tapping screws, so you can drill them into timber without pre-drilling, unless you're going into hardwood in particular. But there are still advantages to pre-drilling. So you get, as I said, you get increased load capacity, particularly when your load's in shear. You get reduced spacing at edge distance and timber thickness as well. It's quicker to install, surprisingly quicker. There's less on-site labour, so it reduces your costs. Pre-drilling can be a locating guide for easy installation as well. Quality control, particularly if your screws are at an angle, you pre-drill at that angle so you know it's going in exactly the right angle into your timber. And on-site, it's a greater battery life as well. So less torque required when you're going into a hole. So they drill a lot more, put a lot more screws in per battery. So just summarise a little bit between Eurocode and NZS 3603. What we're looking at, 3603 looks at joint strength groups based on design densities. I think I mentioned before. Eurocode looks at characteristic densities. So there is a difference between the two, so you need to be aware of that. The characteristic density you saw on those equations are 350. That's for a softwood, probably softer than radiata pine. On testing, we've estimated radiata pine has a characteristic density of about 400, whereas the design density is about 550. So that's the difference we're talking about. In shear, 3603 gives tables which specify characteristic capacities. Eurocode looks at is based on the Johansson's yield theory with the 6 possible failure modes plus the rope effect, as we said. In withdrawal, 3603 really only looks at 2 failure modes. That's head pull through is not considered. Eurocode looks at 3 failure modes, including the head pull through. 3603 has a simplified edge distance and spacing, where Eurocode minimum distances are more complicated, but they're more logical, as I said. And yeah, 3603, all values are applied to pre-drilled holes only. With the Eurocode, pre-drilling is not necessary, but you can calculate for high capacity with a pre-drilled hole. There's something else I thought of, but I can't remember what it was now. Right. Okay. If anybody's interested in other information, we have, you can take my card or leave information if you like. We have done testing on local timbers, so we have a design guide according to NZS 3603, as well as the Eurocode, so you can design either way. There is other information like CLT half-lap joints, things like that. SPAX design guide, there is design software on our website as well. There's a lot of other information out there. Not only just us, if you're going looking at Rotoblast or Worth or one of the others, they've got all that information as well. So they have software, they have ETAs and everything else. So all good products. So yeah, and that's basically it. So is there any questions?
Just wondering, you know, with your withdrawal mode, you have 3 failure modes, and then the failure mode number 3 is the maximum of the pull-out when it goes through the head or the threads,
Yep.
and it's the maximum of the 2.
Yep.
Is there any situation when it actually is the largest, like going to pull through the head rather than the thread? Does that make sense? You said like how you said it's the
Yeah. Okay. So if it's a fully thread screw, yeah, there could be. If the thread, there's not a long thread, so it's a fairly small piece of timber. Yeah, it could be. I think I've calculated it's about 3 times the diameter or something. So if there's only a small amount of thread in there, it can be the actual head pullover. Yeah. The other way, if it's just a partial thread, it's always the head pullover. Yeah. Is that the answer?
Yeah.
Okay. Yeah.
You have a connection where the 2 screws are intersecting. So in that scenario, if you have the capacities, that you stagger them. So you don't have, is there like an interaction?
No, there isn't actually. Because they're actually crossing, there's no actually interaction. You can get.
Is there perpendicular?
Yeah, that's right. The distance is only 1.5 times the diameter, so they can be very close. So if you can drill that close together, good luck. But yeah, so practically it's a bit hard getting 1.5 times the diameter apart. But yeah. Yeah.
What's the availability like for the screws? Do you like a catalogue thing? Because obviously you've got a wide variety of occasions when you use your product, but
Yeah.
you know what screws you can get.
Yeah.
Everything.
Yeah, good question. We have a warehouse here in Auckland. We supply direct to major projects. We supply direct to Incline, for example. But we also sell through placemakers and ITM. Placemakers have a very good range. They don't have a total range, but they can always get it in for you as well. So generally speaking, yeah, it's pretty good availability. But you just ring our office, or we have a new website coming shortly, so they'll have a good store locator as well. So,
how do you compare Eurocode timber quality with New Zealand quality?
good question.
Because there's a huge difference.
That's right, yeah. That's why we did testing on local timbers. So the 3603 design is based on testing that we did. So you'll find the design is the same as 3603, just with different withdrawal figures and shear figures based on the testing. So generally it's a little bit higher than the European figures.
The pine in Europe takes 100 years to grow to the same size, so
Yeah.
it's logical.
Yeah. Yeah, it's always hard when you're trying to compare the two. Yeah. So that's something you need to be aware of, for sure. Yeah. There's a lot of CLT coming in from Europe as well, into Australia and New Zealand. Yeah.
Any other question? Durability, using them in an outdoor application where the codes are full for stainless steel.
Yeah.
And I seem to remember that some of the products are not available in stainless.
Yeah.
Is there a way of getting around that?
Well, that's one reason we have the Delta Seal coatings. The Delta Seal was basically developed for Australia and New Zealand because of our treated timber. Nowhere else in the world has that. So it was developed for that.
Do you have some sort of documentation that we can provide? I know cases where council have said, oh no, sorry, it's going to be stainless steel.
Yeah, we've got test reports on the corrosion resistance, yeah. Yeah, that's, if you really need that, that's clear. A lot of our screws we do have stainless as well, but it's obviously not the same sort of range. Yeah, I know what you're saying. You don't have the same range as in other products. Yeah. So unfortunately, that's the way it has to be. Yeah. Yeah.
Did SPAX consider cyclic loading of testing screws, like in connections?
Yeah, it's never actually been done. No, I think they rely on using safety factors to do that. Having said that, Canterbury University, they're doing a little bit of testing at the moment. They're on seismic, etc. We're supplying a lot of screws to them, so it'll be interesting to see what they come up with. But so far, they've said basically they work really well in the seismic applications from what they expected.
Using the SPAX screws?
Yeah, yeah. But specifically, there's not been any cyclic testing done on them, which I think is a pity. It'd be great if there was, but one day, hopefully, it'll be done.
So best to use all catalogue figures, or just use the figures in the code and the screws are better?
the
We should be using more catalogue figures, or should we be using standard code and saying more screws are better, so that
you can. I mean, depends which way you want to go. If you want to design according to Eurocode, that's generally accepted. And if you want to use 3603 as it is, you can. Just remember that that looks at shank diameter, so you need to look at what our shank diameter is. Or you can use our modified 3603 with the test results. That's probably the best way to go. Yeah, if you want to use NZS figures, yeah. So there's basically three ways you can go. As long as you stick with that method and not interact with the two different parts.
and make sure we get the right screws on site.
Sorry?
How do we get, make sure we get the right screws on site?
Oh, that's right, yeah. Our screws have the washer head and the countersink. They've got the length actually written on the top, so you can see what screw has actually been placed in there, so you can check it as well.
For the wheel screws, what about durability issues if stainless steel is required? Like a requirement for the design?
Yeah.
And they're like for decks or for open structures?
Yeah.
Like you need to use stainless steel screws.
Yeah.
They will produce stainless steel?
Yeah, yeah. You talk about decking and things like that.
Yeah.
Our biggest selling screw is a
big
deck.
arches.
Yeah.
Open
yeah.
arches.
Yeah. Timber Lab, people like that use a lot of stainless steel, not just them actually. The ground control, and our biggest selling screw overall is a decking screw, which is only available in stainless anyway. Yeah.
Is it like in New Zealand or worldwide? So it's best selling in New Zealand or worldwide?
Probably New Zealand and Australia. Yeah. Yeah.
How's the comparison between the two codes for serviceability?
For serviceability?
Yeah, with the Eurocode and the 3603.
Yeah, I haven't actually compared them, to be honest. I think you're looking at your modification factors and things that can be quite different. I don't think there are a huge difference between the two, but I haven't actually compared them directly, to be honest.
But when you look at that flip of the test load and share, there's quite significant displacement between the two members.
Yeah.
And that we wouldn't work in a lot of cases for design.
Yeah. Well, that's you're looking at I think it's 2.5 mil displacement in shear. So that's the local standards. I think that's what they're looking at. But I don't know how the Eurocode looks at that, to be honest. But that's considered in a 3603 design as well.
So when's the new 3603 coming up?
NZS 1720. Good question.
Change the number.
July?
July.
Really? Yeah. Okay. I'll be surprised if it is. Nobody's on the board anyway. I think there was some significant issues with it, but I don't know whether they've addressed those or not. But I won't go into that. Yeah. But yeah, 3603 was very basic and old. Obviously, so yeah, needed something new for sure. Yeah.
You bring any screws with you?
Sorry?
You bring any screws with you?
Yeah. Get rid of that. Now they're screws. Yeah. And they're short ones. Yeah. your cylinder head screw. Or that one. That's a washer head. And your countersunk as well. So, yeah. What do you want? I can give you a short one as well. I've got a few samples there if anybody wants anything. That's all right. Not a problem. If anybody needs any other information, you can either take my card or leave your details, leave my card, whatever. I can email some stuff through to you.
How do you get them in accurately so long?
Well, that's when pre-drilling comes in. It's handy, but if you're just going straight in, it's generally not a problem. That'll drill straight in without a problem into your tine, in particular. No need to pre-drill. But yeah, if you're going into hardwood, you really need to pre-drill. And if you're going in a specific angle, that's when you really want to pre-drill as well.
So you usually just pre-drill in the first piece?
You can do just it was just right out of pine, just a pilot hole, maybe 50 millimeters or something. That's all you need. But again, if it's hardwood, the whole length of the screw. Yeah. Yeah. Okay.
Well, thank you, Greg, for your time tonight. I'm sure we'll all learn a lot from the presentation.
Hope so.
Not sure how you brought that over. I mean, surely it's not in the carry-on or these things.
Definitely not.
But on behalf of Open Structural Group, we'd like to show our appreciation. Thank you so much.
Thank you. Thank you.